Hi everyone, hope you're doing well. Today we are moving on finally and we're going to talk about some new information, polar bonds. You should have your notes open to this page. Figuring out if a bond is polar, non-polar, and if a molecule is polar or not is sometimes tricky for a lot of students and throws people off. And so I hope with the online videos you can rewatch things. Maybe you missed what I said. You can pause and rewind. Please use that to your advantage, and I think hopefully we should do a little better having everything online this year. But as we go through this today, I will need you to be focused, and this lecture will be a little longer than normal. Okay, so in our notes we should be at this page. So do we remember electronegativity? It is a measure of the tendency of an atom to attract a bonding pair of electrons. That word bonding pair of electrons, that refers to like the electrons in a single bond or a double bond or a triple bond. It's not talking about any other electrons. So let's say I have carbon and oxygen. Here we go. That's not even the correct Lewis structure. It's actually a triple bond, but there we go. The bonding, okay, now that that's right, the bonding electrons would be these guys, not those. So we're talking about the single bonds, the double bonds, as I said. And this table is the table we're going to use. It has electronegativity values for just about everything. Fluorine is the most electronegative atom with a value of 4.0 compared to cesium and francium down here are 0.7. Hopefully you can see our metals have a low electronegativity value. Our nonmetals have higher electronegativity values. Okay, and so that definition, electronegativity, they attract a bonding pair of electrons. What does that mean in normal terms? So let's say I have carbon and fluorine bonded together. Carbon has an electronegativity of 2.5, fluorine 4.0. So they share electrons, they're nonmetals, that's a covalent bond, but even though they're sharing, fluorine's going to attract the electrons more because it's more electronegative. And what that would look like, let's say we had carbon and fluorine with a single bond. So fluorine attracts that single bond. Well, that single bond is 2 electrons, and so really what it looks like is here's my carbon, here's my fluorine, and here's my little electrons, negative, negative. They spend more time with fluorine than they do with carbon because fluorine is more electronegative. So that's what that definition means. I hope that makes a little bit of sense. Okay, and electronegativity is used to determine what type of bond something has. So when two atoms have a large difference in electronegativity, typically the electronegativity is greater than 1.7, they form an ionic bond where they actually transfer the electrons. That usually happens with metals and nonmetals. Because that value is so big, that nonmetal just takes the electrons. But when the electronegativity difference is relatively small, between 0 and 1.7, they form a covalent bond, which means they share electrons. Now there are two types of covalent bonds. We have nonpolar covalent bonds, where electrons are shared equally between atoms, and then polar covalent bonds, where electrons are not shared equally between atoms. And that's determined by their electronegativity difference. So if the difference is between 0 and 0.4, it's nonpolar covalent. 0.4 and 1.7, it is a polar covalent bond. So nonpolar, they share them evenly. Polar, they don't share them evenly. And if I were to draw it, let's say C and H are a nonpolar bond. And it's a single bond between them. What it would look like is my electrons are in the center, nice and happy, being shared by both, versus that carbon and fluorine example you saw, which is actually a polar bond. The electrons are over by fluorine and not by carbon. So nonpolar, they get shared equally. Polar, they don't get shared equally, and it's based on their electronegativity difference. We're going to practice figuring out what type of bond would form between atoms with these 4 examples. And then we're going to circle the more electronegative atom. So let's get started. P and Cl. P, our phosphorus, has an electronegativity value of 2.1. Why did I say phosphorus? Chlorine. Chlorine has a value of 3.0. And so my little table is right here to help. 3.0 minus 2.1 is a difference of 0.9. And so that is a polar covalent bond. And then circle the more electronegative atom. Well, it is chlorine. Next, K and F, potassium and fluorine. Potassium has an electronegativity value of 0.8. Fluorine has a value of 4.0. 4 minus 0.8 is 3.2. So that falls under an ionic bond. And then who's more electronegative? Fluorine. And so with that ionic bond, potassium actually gives fluorine its electrons. Well, or you could say fluorine takes the electrons because it's so electronegative. Next, I'll use purple. Br and Br. Well, bromine has an electronegativity value of 2.8. Bromine has an electronegativity value of 2.8. That difference is 0. So that is a nonpolar covalent bond because they have the same electronegativity. So they share electrons equally compared to the P and Cl where they're not shared equally. And so for this one, there's not a more electronegative atom for me to circle. I'm going to erase this so I can do my last example. So if you want to pause right now, I'm erasing next. Okay. And last, my N and my H. Nitrogen has an electronegativity of 3.0. Hydrogen, 2.1. 3 minus 2.1 is 0.9. So that is a polar covalent bond as well. And the more electronegative atom is nitrogen. So the electrons spend more time with nitrogen than they do with hydrogen because nitrogen attracts them more. So this is how you figure out what type of bond something has. You just have to go to this table, look at the electronegativity values, and subtract them. This slide is not in your notes, but I like this picture, well, these pictures, because they show what is going on and how electrons are being shared or not shared. So starting on the left, we have Cl and Cl. That's a nonpolar covalent bond. They're the same atom, so their difference is 0. And our bonding electrons, so that's those 2 atoms right there, they get shared equally. Versus a polar covalent bond like HCl, they're not shared equally. The more electronegative atom hogs the electrons. They spend more time with him. And so inside the little molecule, you can see that arrow is larger pointing to chlorine. Chlorine is more electronegative as your table shows. So the electrons are more over with chlorine than they are with hydrogen. Versus an ionic bond where they are completely transferred. And my Na actually gives chlorine the electrons. So we can see the difference between the 3. Now, something you may or may not have noticed, this with the covalent bonds, it says for a nonpolar covalent bond, there's no charge on an atom versus a polar covalent bond, there are partial charges on atoms. What does that mean? A partial charge. That means my more electronegative atom, it has the electrons closer to it, so it is partially negative. Electrons are negatively charged. It has It's not sharing them equally. It has the electrons more over with it. So it's not fully negative like the chlorine in that ionic bond. It's partially negative because it kind of has electrons, more electrons than it normally does. And then my other atom, my hydrogen, is partially positive because it should have those electrons close to it, but it doesn't. And so my H becomes partially positive, my Cl is partially negative, and it's the more electronegative one that it is partially negative because the electrons are more with it, leaving the other one partially positive. And that is what these symbols represent: partially negative on the right and partially positive on the left. It's not fully positive because it's not an ionic bond. The full only goes with ionic, but it is partially charged. Okay, so now that we've discussed that, you saw those symbols. So from now on, when you draw a Lewis structure, if there is a polar bond, you have to draw on the Lewis structure one of these symbols. And there are two ways to represent that it's polar. Now this is only for polar bonds. If it's not a polar bond, you don't draw the symbol, only when it's polar. And so you saw on the slide before, that is a Greek letter. I don't remember which one, doesn't matter, but the little Greek squirrely and the negative sign goes on the partially negative atom, which is the more electronegative one. The little Greek squirrely with the plus sign goes on the less electronegative atom. And that represents that that atom is partially positive. It kind of lost its electrons, but it hasn't totally lost them. So you can do those swirlies, or you can draw this arrow. And that arrow points to the more electronegative atom. So it doesn't matter which one you use, but if it's a polar bond, you have to draw it on your Lewis structure. So this would be, let's say I told you draw the Lewis structure of CF4. You draw your structure first, and then you're going to add these symbols onto it. And so below, you have some examples of Lewis structures. We're going to draw them together. So first, CCl4. If I were to draw that one's Lewis structure, I need to go figure out, is that C and Cl a polar bond? So go to my chart. Carbon's got an electronegativity value of 2.5. Chlorine, 3.0. Not 3.5, 3.0. 3 minus 2.5 is 0.5. So that is a polar bond. Each one of these, that's a polar bond, that's a polar bond, that's a polar bond, that's a polar bond. So if I asked you how many polar bonds are in CCl4, you would say there are 4 polar bonds. All of those bonds are polar because the difference is 0.5. And so if we were to add our symbols, on the left we'll do the arrow. The arrow points to the more electronegative one, which is, looking back, chlorine. So I just literally draw it in. And I have to draw it in 4 times. You draw a symbol for every polar bond, and it points to the more electronegative one. If I were to do the little Greek thing, okay, chlorine's more electronegative, so it gets the partial negative. And I literally just draw that little symbol next to all of the chlorines, and then next to the carbon, a partial positive. And you just have to draw it once for carbon. So that is what I'll be looking for from now on. And again, we only do these symbols if it's a polar bond. If this was a non-polar bond, we wouldn't draw symbols. You would just draw the Lewis structure and move on. We only do this for the polar bond. Another example, OCl2, and let me change from that yellow. Okay, so I go to my table. Oxygen's electronegativity is 3.5. Chlorine's electronegativity value, 3.0. 3.5 minus 3.0 is 0.5. So that is a polar covalent bond. And so we need to add symbols. Okay, I don't have coronavirus, I swear. At least not that I know of. So, who's more electronegative, oxygen or chlorine? Oxygen is, so I'm going to draw the arrow to my oxygen on both bonds because that's a polar covalent bond, that's a polar covalent bond. And if I were to do the little symbols, boom, negative, positive, positive. And then you would circle it and just about be done. There's the Lewis structures. Again, it doesn't matter which symbol you choose to use. You don't have to do both. You just pick whichever one you like better, but you only draw these symbols if it is a polar bond. And last one. This one is a little trickier. So we've got H2CO. Well, in this Lewis structure, we've got a carbon and a hydrogen bond. And then we've got a carbon and an oxygen bond. And so we've got two bonds to figure out. Okay, so going to my electronegativity table, hydrogen's electronegativity value is 2.1, carbon 2.5, oxygen is 3.5. So first the carbon-hydrogen bond, 2.5 minus 2.1 is 0.4. And so that's going to be a non-polar bond. And because it's non-polar, it has no symbols. You don't draw anything on the CH bond. So that was easy. But let's look at the CO. Oxygen is 3.5 minus carbon, which is 2.5. So that's an electronegativity difference of 1. That is a polar bond. And so we have to draw symbols on the CO. Now, it does not matter if that's a double bond, a triple bond, a single bond. You don't change the way you subtract them. You still just look at the periodic table and subtract them. If it was a single bond between C and O, it would be the same thing. Now I'm going to erase this really fast. Okay, so I just have to draw symbols on my CO bond. So, and oxygen's more electronegative, so my arrow goes to O, or if I did my Greek symbols, partially negative on oxygen, partially positive on carbon, because there's only one polar bond. The CH bond is not polar, so it does not get symbols. Today, we've gone over quite a bit. We've reviewed what does electronegativity mean, the difference between nonpolar covalent and polar covalent. And so to review, nonpolar covalent, the difference is between 0 and 0.4. That means electrons are shared equally. There's no partial charge and no symbols drawn. It's all no. Versus a polar bond, it's the difference between 0.4 and 1.7, and that is where electrons are shared unequally, which makes a partial charge. And there are symbols drawn on the Lewis structures. The quiz you're going to go take is not an actual quiz grade, but it is to review the notes, make you think a little bit about what we went over. You know how we do practice in class? Well, this is like your practice now, so I can see what did you understand and what did you not understand to make sure for Monday, well, next week, that I can clear up any misconceptions. So please use your notes on it. Please, well, you have to take it. That's not an option, but do your best on the quiz so I can figure out what we need help with for next week. I hope you have a great weekend and that none of you get coronavirus and that we all stay very healthy.